Days of Chemistry, Part 13, this time looking at 9.2.2 Biomass and Biopolymers. Now, the key idea behind this whole section is the logic of this whole 9.2.2 section, and it actually incorporates 9.2.1, which is about polymers, 9.2.2, which is biomass and biopolymers, and 9.2.3 ethanol. It probably would have been better in hindsight to go from 9.2.1 to 9.2.3 ethanol and then back to biomass, and the reason being, let's go through the logic. Well, first of all, we know that fossil fuels are used for fuels, they're also used for petrochemicals. But we also know they're running out because they're non-renewable, they're polluting, and the petrochemicals we make from fossil fuels are non-biodegradable. So there's some problems with fossil fuels. So what are some of the solutions? As we learned in 9.2.3, one of the solutions is to make ethanol. Now, ethanol can be made from fermenting sugar, and therefore it's renewable and theoretically carbon dioxide neutral. Ethanol can be burned, therefore ethanol is a fuel, it's a replacement for fossil fuels. But also ethanol can be dehydrated, is something we learned, to make ethylene or ethene. And we know that ethene is the precursor chemical for the whole range of petrochemicals. So that means we can actually make ethene renewably, and once we can make ethene renewably, we can replace all petrochemicals. So that's an advantage of ethanol. But there's some problems with ethanol we learned too. First of all, there's limited sugar supply. It takes farmland to grow sugarcane and sugar, and therefore you lead to the whole food versus fuel debate. And also sugarcane can only be grown in certain climates. This is why Brazil has been so effective using its ethanol fuel, because it's got the climate that can grow sugarcane, but not everyone in the world can grow sugarcane and get sugar directly to make ethanol directly. So there's some problems there. And also the polymers we make from ethylene, even if it's bioethylene, the polymers themselves, we make polyethylene from this ethene here, it's still going to be non-biodegradable polymer. So there's some problems with using ethanol. So what's an alternative solution? And one of the things that people are looking at is this solution here, which is to use biomass. And why do we use biomass? Because biomass is mainly cellulose. It's more abundant than sugar. All plants have cellulose, which we can extract, whereas not many plants have that high sugar content we can extract sugar from. It's found in waste materials, and because we can use cellulose, we can use less food, farmland, and there's a greater supply of cellulose than there is of just glucose. And if we need to, we can convert cellulose into glucose. So we can get cellulose, we can make it into many useful products, and that means that we're going to solve some of these issues that ethanol was facing. In addition, there's other sorts of biomass as well we can use, such as biopolymers, which are biodegradable. But one thing to note, this whole section on biopolymers and cellulose is still in the development stage. People aren't actually using cellulose to make huge amounts of petrochemical replacements just yet. This is all sort of theoretical sort of topic. So let's look at this section here. Biomass and cellulose and condensation polymerization. Biomass is basically matter sourced from living things, and plants make up the bulk of biomass, and cellulose makes up the bulk of plants. So cellulose makes up the bulk of biomass. And cellulose is a condensation polymer of glucose monomers. Or what's a condensation polymer? It's a polymer made by the reaction between monomers, which eliminates a small molecule such as water during the reaction. Now, glucose is produced by photosynthesis, and that's it, and then the cellulose are renewable. And there's the reaction for photosynthesis. You need to remember that equation. And one thing you should be able to do as well is we often write glucose as C6H12O6. But in Year 12 chemistry, you should know the actual structural formula of glucose. This is the way I taught myself to remember glucose. It's a hexagon or a hexagonal ring. We start with our carbons. We're going to draw some carbons in a hexagon. So 1, 2, 3, 4, 5. But the last spot is not a carbon, it's actually an oxygen. So just to remind myself, that top right corner, I'm going to put an oxygen. So it's like a hexagon of carbons, except one of those carbons has been replaced with an oxygen. Now this top left, we've done the top right as oxygen, the top left is not going to miss out. It's got a special group here. It's going to be a CH2OH group is sticking off the top of that carbon there. Now every carbon around the chain is going to have something else sticking off. This one was sticking upwards, the next one must be sticking downwards. It's going to be a hydroxyl group. So that first carbon gets something special, the rest all get the same. It's all hydroxyl groups. One up, one down, one up, one down. We're going to finish off the last one. It's going to be sticking up. There's our hydroxyl group there. So CH2OH, OH, 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 OH. Now to finish off the chain, every carbon we know needs 4 bonds, and that means all these carbons, they've currently got 3 bonds, they need one more bond, they all need an extra hydrogen to finish off their bonding. So we'll put a hydrogen on all these carbons. And now, have we got the C6H12O6? Let's go count our carbons. We've got 1 up there, 2, 3, 4, 5, 6. There's our 6 carbons. Let's count our hydrogens. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Our 12 hydrogens are there. And finally, let's look at our oxygens. Have we got our 6 oxygens? 1 up there, 2, 3, 4, 5, and 6. So C6H12O6. In order, it was the hexagon, then the oxygen in the top right, the CH2OH in the top left, and that's pointing up. Then every carbon after that's going to have a hydroxyl group. That was pointing up. The second one's going to be down, up, down, up. Then we just put the extra hydrogens on the carbons to make up the carbons for bonds. That's how you draw glucose. Why have we got to be able to draw glucose? Because glucose is the monomer for cellulose. If you want to draw the cellulose molecule, you need to know the glucose molecule. One thing to be aware of is that when you're making cellulose, every second glucose is inverted. So we can see here is the glucose we drew with the CH2OH sticking up. The next glucose has the CH2OH sticking down and the oxygen at the bottom right. It's just been completely flipped upside down to react. And the reason being is when they're flipped upside down, that puts these 2 hydroxyl groups together side by side so they can react, they can release water. If we take out a water molecule from OH and HO, we're left with 1 single oxygen, and that oxygen forms a little bridge, and the oxygen forms 1 bond with the carbon there and 1 bond with the carbon there, and that's oxygen that joins the 2 monomers together, and the water leaves, hence being a condensation reaction. Now, one trick they've put in the HSC in the past, just be aware, if you're reacting N glucose monomers together, you're going to get N-1 H2O's released, and that's because, for example, here we've got 3 glucose monomers. When you've got 3 monomers though, there's only 2 bonds being formed. There's always 1 less bond than there are monomers, hence you get N-1 water molecules released. These pictures here are just showing you a whole lot of pictures of cellulose. Here's like a ball and stick model. Here's what it actually probably looks like with the atoms very, very close together. And here's a whole lot of cellulose chains side by side. It might be hard to see, but they fit together quite nicely. And all these hydroxyl groups sticking off the outside of the cellulose make very strong hydrogen bonds between the cellulose chains. So cellulose has got strong covalent, not covalent, it's covalent intermolecular bonds, and lots of intermolecular hydrogen bonding between the chains, which means cellulose is very strong, but it's also difficult to break down, which makes extraction of glucose high energy and high cost. You need crushing and grinding, bacterial digestion to break down the cellulose into glucose, or hydrolysis with acid. Wish I could spell that properly. And that's to separate the cellulose into glucose. And then you've got the separation techniques to extract the sugar out of that mixture, and then you can go on with the fermentation, dehydration. So it's quite energy and process intensive. So what are the uses and potential of cellulose? Well, first of all, cellulose itself can be used as a fuel. You can burn it because cellulose is basically wood. Cellulose is naturally made into cotton and linen by the cotton and flax plants. It can be converted into polymers such as cellophane and rayon, and you can actually hydrolyze, as we said before, cellulose into glucose, and therefore it greatly increase the availability of this resource. So any ag waste, not just cropland, can in theory be turned into glucose, which then can be turned into ethanol and then bioethylene. So what are the key ideas? Cellulose is abundant, cellulose is renewable, and cellulose contains the basic carbon-carbon structure to make replacement petrochemicals. That's that phrase straight from the syllabus. But don't forget, lots of research needs to be done still to make this conversion of cellulose into useful materials cheap, energy efficient, and high volume to make them compete with current petrochemicals. We're not there yet. This is something that's hopefully going to happen in the future. The last part of 9.2.2 was looking at an example of biopolymers. One of the big drawbacks of petrochemical polymers, or polymers made from ethanol-derived ethylene, is they're non-biodegradable, which leads to landfill and wildlife problems. And so what's a biopolymer? A biopolymer is a polymer derived from biomass. So technically cellulose is a biopolymer, but the one we studied was PHB. Now PHB is polyhydroxybutanoate. It's a biopolymer originally made by Eutropis bacteria, but it's now being made by GM E. coli and GM plants. Here is the polymer, PHB, and here are some of those bacteria. You can see these little tiny white sort of sphericals inside these little bacteria. That's the PHB granules being made inside the bacteria. Now, why PHB? It's got properties similar to polypropylene, which is one of the most commonly used petrochemical polymers, but it's also biodegradable, it's also biocompatible. It's currently being used in surgical sutures because of its biocompatibility, disposable bottles and razor handles. Here's some example bottles that have actually been made of biopol or PHB. As you can see here, over time, they do degrade and start to break down in the environment. They are biodegradable. One of the big advantages of PHB over many other biopolymers is it's non-water soluble, and therefore it can last in situations where it needs to be in contact with water or moisture. Only problem with PHB is compared to the amount of petrochemical polymers being made, its production is still very small. It actually can be quite expensive compared to normal petrochemical polymers as well, and it's only got a limited number of properties itself, and therefore it can't replace all the different petrochemical polymers used. The key idea here is it needs to be one of the many biopolymers that we develop in the future to replace petrochemical polymers.